So last time we stopped here where we were enlisting the properties of monotone functions. So monotone functions can only have countably many discontinuities. The discontinuities are simple jump discontinuities. The monotone function is Riemann integrable. Given any countable dense subset D, there is a monotone function which is discontinuous precisely at the points of D, and a monotone function is differentiable almost everywhere. Of all these properties, fifth is deep, and the proof is available in Roydin's Real Analysis, Chapter 5, as an application of the Vitali covering theorem. It's an excellent book, and I'll leave it to you to consult Roydin for property 5. Let us look at properties 1, 2, 3 and 4, because most of what we are going to say will go over for monotone functions in general, and we can weaken the hypothesis of our theorems in Fourier series considerably. So let us see how bad a monotone function can be in terms of continuity. So to prove that a monotone function has only jump discontinuities, so let us take f from AB to R, which is monotone increasing, say, and let us take a point C in the interval AB. What we do is that we take L to be the infimum of f of t, where t ranges over the interval CB, open on C and closed at B. So this infimum obviously exists because f is monotone increasing, and we are going to show that the function f of t approaches L as t approaches C from the right, which proves the existence of a right limit. So the existence of a left limit will be exactly similar. So let epsilon greater than 0 be arbitrary. Then by the definition of infimum, there exists a t naught such that f of t naught less than L plus epsilon, and t naught belongs to the interval CB, C excluded. Then by monotonicity, we know that L is going to be less than or equal to f of t, and f of t is going to be less than L plus epsilon whenever C less than t naught. This just comes from monotonicity. So the requisite delta that we are looking for is t naught minus C. So given in epsilon greater than 0, there is a delta greater than 0 such that L less than f of t less than L plus epsilon whenever C less than t less than C plus delta. So the proof of the existence of a limit from the right is established. The proof of the existence of the limit from the left is also similar, and we look at the supremum of f of t where t varies between A and C, C excluded. That's the idea. And the next thing that we need to do is that f of C minus is less than or equal to f of C plus. That also is very clear. Suppose, for example, we take A less than or equal to C1 less than C2 less than or equal to B. Then supremum of f of t, where t ranges from C1 to B, that is going to be less than or equal to infimum of f of t, where t ranges from C2 to B. This again comes from monotonicity. So we again conclude that f of C1 minus, which is less than or equal to f of C1 plus, is going to be less than or equal to f of C2 minus, which is less than or equal to f of C2 plus. So the point is, if you take two distinct points C1 and C2, then the right limit at C1 is less than or equal to the left limit at C2. So we have this chain of inequalities. So suppose if C1 and C2 are 2 points of discontinuity, then the intervals LC1, which is f of C1 minus, comma f of C1 plus, and the interval LC2, which is f of C2 minus, f of C2 plus. These intervals are disjoint, non-empty, open intervals. They are non-empty because we have assumed that C1 and C2 are discontinuous points. So the left limit and right limit are unequal, and so these intervals are open intervals. They are disjoint by the previous chain of inequalities. So now we got the fact that when C1 is less than C2, we got these intervals LC1 and LC2 are disjoint. So out of each of these LCs, so for each point of discontinuity C, we have this interval LC, which is an open interval. In this open interval, you pick a rational number. Call that rational number QC. So out of each of the intervals LC, I picked up a rational number QC. If you take C1 less than C2, the intervals LC1 and LC2 are disjoint, so QC1 and QC2 are distinct. So if C1 is not equal to C2, then QC1 is not going to be equal to QC2, which basically means that the function Q that we have constructed is injective. So we have got an injective function from the set E of discontinuities into Q, and since Q is countable, E must also be countable, and we have proved both results that the set of discontinuities of a monotone function is at most countable. Second, the discontinuities are simple jump discontinuities. They are not of a more complicated kind. Okay, now the Riemann integrability of a monotone function also follows at once. How does it follow? When is a function Riemann integrable? Recall from real analysis that a function is Riemann integrable if and only if the set of discontinuities has Lebesgue measure 0. Because our set of discontinuities of a monotone function is actually countable and every countable set has Lebesgue measure 0, the set of discontinuities of a monotone function has Lebesgue measure 0, which means that a monotone function is Riemann integrable. Of course, you can also give an elementary direct argument for the Riemann integrability of a monotone function. I'll leave it to you to look at the standard books on Riemann integration and consult it. A one-line argument will be to use the theorem on necessary and sufficient condition for Riemann integrability. Again, repeat that the set of discontinuities can be any countable set, and that's what we are going to establish now. Suppose if E is any countable dense set of AB, you enumerate this countable set, E equal to R1, R2, R3, etc. What we do is that take any series of positive terms which converges, say a geometric series 1 plus half plus 1/3 plus 1/4 whatever, sigma 1 upon 2 to the power n, take that geometric series. What we will do is that we will construct a function f from AB to R as follows. Define f of x to be summation 2 to the power minus j where Rj less than x. So what are we saying? We are saying look at those Rj's which are less than x. Say suppose if R1 is less than x, R3 is less than x, R4 is less than x and everything else is bigger than x. Suppose that is the situation. Then R1, R3 and R4. So what are the subscripts? 1, 3 and 4. So look at those terms. So take from the infinite series that we have, take the first term, take the third term and take the fourth term and add them up. And that is your value of f of x. So f of x is sum of those terms in the infinite series, sum of those 2 to the power minus j such that Rj is less than x. Now if x is less than y and if Rj is less than x, then automatically Rj is going to be less than y. So when you are computing f of x and you are computing f of y, you compare these two expressions, all the terms appearing in f of x will also appear in f of y, because every time Rj is less than x, Rj is automatically going to be less than y. So f of x is going to be less than or equal to f of y. So the monotonicity of this function f of x is evident. It is not difficult to verify, and I'll leave it as an exercise, that this function is continuous on the complement of E, and E is exactly the set of discontinuities of the function f. We leave the details to you. So the structure of discontinuities has been completely clarified for a monotone function. Now I could take the set E to be the set of all rational numbers lying inside AB. So here I have a function which is continuous at all the irrationals sitting inside AB and discontinuous at all the rationals sitting inside AB. So the set of discontinuities can actually be dense. So now one more comment is that this raises a question. Can you have a function f which is discontinuous at irrationals and continuous at rationals? Answer is no. The set of points of discontinuities of any real function has to be an f sigma set, a countable union of closed sets. And the rationals form an F sigma set, irrationals do not form an F sigma set, they form a G delta set. That's just a side comment at this stage. Now let us come to Dirichlet's theorem on monotone functions. This was the earliest theorem of such rigor and in such generality established by Lejeune Dirichlet. And what does the theorem read? The theorem reads as follows. Suppose f from minus pi to pi is piecewise continuous and monotone. This piecewise continuity can also be relaxed. It doesn't, one can relax these hypotheses. That's why the list of theorems on monotone function has been given. So one can keep relaxing it, but if f is from minus pi to r is piecewise continuous monotone function, then the Fourier series of f converges to f of x at all points of continuity, and at a point x naught of discontinuity, the Fourier series converges to the arithmetic mean 1/2 of f of x naught plus f of x naught minus. That means when you have piecewise monotone continuous function, then at points of continuity, the Fourier series converges to f of x, and at points of discontinuity, it converges to the arithmetic mean of the right and left hand limits. In particular, the Fourier series converges everywhere. Remember that the function is piecewise continuous and monotone. It is the monotonicity of the function that is crucial here, because without monotonicity, if you just have continuity, even if continuity everywhere, the Fourier series will diverge. We have just seen that in module 7. So this is crucial. The monotonicity assumption is critical here. To simplify Dirichlet's argument, Aucy and Bonnet established the mean value theorem for integrals that bear his name. Dirichlet's argument was long, and Aucy and Bonnet's considerably simplified the argument given by Dirichlet. Bonnet's version of the mean value theorem for integrals is not available in many modern texts. It is one of those beautiful theorems that have somehow gone out of vogue, and so it is good to look at this theorem in detail with complete proof, because it's going to be difficult for you to locate the proof in the literature. So let G from AB to R be continuous if f from AB to R is monotone. So you got two functions, one of them is a continuous function and the other one is a monotone function. Then there exists a C in AB such that integral a to b f of t g of t dt equal to f of b minus integral from c to b gt dt plus f of a plus integral a to c gt dt. Now in particular, if f is monotone decreasing and positive, then one of the terms can be knocked out. Then there is a c in closed interval ab such that integral a to b f of t g of t dt equal to f of a plus integral a to c gt dt. On the other hand, if f is monotone increasing and negative, then the other term can be knocked out. So for some c in the closed interval ab, integral a to b f t gt dt equal to f of b minus integral a to c gt dt. This is a complete result. What we are going to do is we are going to first prove the first part of this theorem, and the second and the third will be deduced as corollaries of the first part. So how to do the first part? Before we take up the proof of Bonnet's mean value theorem, let us see how to use Bonnet's theorem and why is this mean value theorem for integral calculus become so critical in the proof of Dirichlet's theorem on Fourier series. So here is a result which we are going to prove using Bonnet's mean value theorem. Theorem 85. Integral 0 to infinity sin omega t upon t dt equal to pi by 2 if omega is positive and is minus pi by 2 if omega is negative. If omega is 0, of course the integral is then 0. So the Signum function is a function that assigns the value 1 if the number is positive, it assigns the value minus 1 if the number is negative, it assigns the value 0 if the number is 0. As a Signum function. So integral 0 to infinity sin omega t dt upon t equal to signum of omega into pi by 2. And the second part is, if you have a monotone function f from 0 infinity to r, then for any s bigger than 0, limit omega tends to infinity, integral 0 to s f of u sine omega u upon u du equal to pi by 2 times f of 0 plus. The first part of the proof is pretty standard. Well, it is enough to prove it for omega positive, because if you prove it for omega positive, replace omega by minus omega and you are done. Now, what you do is that you make the change of variables, omega t equal to u. Then what happens to the integral? It simply becomes integral 0 to infinity sine u by u du, and the value of this is pi by 2. Or equivalently, integral minus infinity to infinity sine u by u du equal to pi. In an earlier module, when we discussed the Airy's equation, we discussed this conditionally convergent integral in very great detail. There I mentioned to you that finding the value of this integral is a completely different matter. We only established the convergence of this integral. We are not established the value of the integral. There are various ways in which you can calculate the value of the integral. One way is very simple, and it is put back the omega. Let us look at it as integral sine omega t by dt, the original integral. The value of the integral is a function of omega. Take the Laplace transform with respect to omega. So, call the integral I omega. Call the integral I omega. Take Laplace of I omega. What is Laplace of I omega? It is Laplace of integral 0 to infinity sine omega t by t dt. Take the Laplace transform inside the integral. It is integral 0 to infinity Laplace of sine omega t. Remember, we are taking Laplace transform with respect to omega. And so, what is Laplace of sine omega t? T by t squared plus omega squared. The t cancels out. We simply have integral 0 to infinity dt by t squared plus omega squared, and we have the value of the integral 1 upon omega into pi by 2. So, Laplace of I omega is pi by 2 into 1 upon omega. So, what is I omega? Pi by 2. Which function has Laplace transform 1 upon omega? 1, the constant function. That is one way of doing it, but there is a small problem with this argument. The problem of taking the Laplace inside the integral has to be carefully justified. We will not discuss that. On the other hand, you already seen this integral in complex analysis courses, how to compute this integral using Cauchy's theorem. The classical way of computing this integral is not using Laplace transform, but rather using Cauchy's theorem applied to e to the power I z minus 1 upon z on a semicircular contour in the complex plane indented at the origin. You can look at any book on complex analysis, and so I leave the details to the audience. So, now let us take the proof of the second assertion in this theorem 85. Limit as omega tends to infinity, integral 0 to s f of u sine omega u upon u du equal to pi by 2 times f of 0 plus. Let us take the proof of this now, and so let us first integrate it from 0 to s. 0 to s f of u sine omega u by u du. Let us add and subtract an f of 0 plus. Okay. So, you get two terms, integral 0 to s f of u minus f of 0 plus sine omega u by u du plus f of 0 plus integral 0 to s sine omega u by u du. Now, let us look at the second piece. In the second piece, let us put omega u equal to t, and what happens? Sine omega u by u becomes sine t by t, and when u equal to s, the upper limit becomes omega s, and when omega goes to infinity, we simply get integral 0 to infinity sine t by t dt, and that is pi by 2, and so the second piece has been taken care of. Now, let us tackle the first piece. So, let epsilon greater than 0 be arbitrary. Now, select an r bigger than 0 such that mod f of u minus f of 0 plus less than epsilon by a for 0 less than u less than or equal to r. It's a limit definition I have applied. F of u approaches f of 0 plus as u approaches 0. So, take an epsilon greater than 0, there is a corresponding delta denoted by r. A is a certain constant that will be specified presently. Then what happens to integral from r to s f of u minus f of 0 plus upon u sine omega u du. It goes to 0 by Riemann-Lebesgue lemma. The piece from R to S. The piece from R to S. R is fixed and S is bigger than R. Then that ratio f of u minus f of 0 upon u is continuous because we are far away from the origin. And so simply Riemann-Lebesgue lemma applies. And so we are left with the piece 0 to R f of u minus f of 0 plus upon u sine omega u. Here we apply the Bonnet's mean value theorem. F is monotone. F is monotone. So we apply the Bonnet's mean value theorem and we get f of r minus f of 0 plus integral from c to r sine omega u by u du for some c. Since the integral term is bounded in absolute value because the integral converges, we see that integral from 0 to r f of u minus f of 0 plus upon u sine omega u du is less than epsilon in absolute value. So the a that we appeared earlier is the absolute value of the integral converges. So proof is completed. So now we will prove the theorem of Bonnet, and the proof is available in Gibson's Advanced Calculus, but the proof is an exercise in Gibson's Advanced Calculus. So we will work out this exercise basically. So for convenience, I restated the first part of Bonnet's mean value theorem for integral calculus. F from AB to R is monotone, G from AB to R is continuous, and then there is a C in the interval AB such that integral A to B f of t gt dt equal to f of B minus integral C to B gt dt plus f of A plus integral A to C gt dt. Okay, so I stated it again just for convenience. So what is the idea? The idea is to write the integral on the left hand side as a Riemann sum. So let us write the integral as a Riemann sum and we get a finite sum, and on this finite sum we must apply Abel's summation by parts. So what is the rule for summation by parts? This is a beautiful application of the rule for summation by parts. The rule for summation by parts is simply the discrete analog or the rule for integration by parts. And this summation by parts formula is used very frequently when you are dealing with conditionally convergent series. So suppose if a and b are two sequences, then summation j from 1 to n aj into bj minus 1 equal to summation j from 1 to n with a minus sign thrown in aj minus 1 bj minus 1 plus an bn, with the understanding that a0 equal to 0 and b0 equal to 0. Okay, this is the simple identity, and this identity is absolutely trivial. You can just completely do it by just writing out the two sides and verifying the correctness of this. Observe the analogy for the rule for integration by parts. So how do we use this rule for summation by parts? Okay, so now let us assume that f is monotone decreasing. So the product fg is Riemann integrable. You see, if f is Riemann integrable, g is Riemann integrable, the product is always Riemann integrable, g is continuous and f is monotone, both are Riemann integrable. The idea is to approximate the integral of fg by its Riemann sum and apply the rule for summation by parts and pass to the limit. Let us begin with the integral on the left hand side, integral a to b ft gt dt. So on this integral on the left hand side, we write the Riemann sum. The Riemann sum r of fg comma pi. Script r denotes the Riemann sum of fg and capital pi denotes the partition of the interval. So that is summation j from 1 to n f of cj g of cj tj minus 1. How to choose the cj? To choose the cj, observe that g is assumed to be continuous. So the mean value theorem for integral calculus says that integral gu du from tj minus 1 to tj is g of cj into tj minus 1 for some cj in the open interval tj minus 1 tj. Because g is continuous, this is possible. It is this cj that we use in the Riemann sums. So now we shall see how to do this, continue by applying the rule for summation by parts in this finite Riemann sum. We will return back to this in the next lecture.